Cool. So induction motor. So basically what it does, just to keep it like real simple, so you can just understand the bigger picture, is well you all know the three-phase motor. So basically the first thing, it just taking three sine waves. So you have one sine wave like this, you have another one here, and then you have another one starting at the bottom. So, and all of these three things kind of together into one wave, right? But all this is a three-phase supply, and what the three-phase supply is just three sine waves 120 degrees apart spatially. So this is at 0 degrees, this is at 120, and this is at 240 degrees. All in all, it just is just three sines that are 120 degrees apart, which is basically just three-phase power. So you have three phases coming into a motor. And in the motor itself, you have three phases, which are 120 degrees apart, or you can say three coils of wires. Right? So you have a north, south, then pow, 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 go across there. So then here you have a south and a north, and here you have a south and a north. So I use different colors because I kind of use the same. So black, so that's your first phase. Then you have red, then you have a next one, probably like green. So these are coils. So you have one pole pair, two, and three. Okay? And when you supply the power, so you have your green power, which apply in a green phase, then you have your black, then you have your red, and well, your three phases going into it. So your three phase power going into the supply. So one phase, the second phase, and the third phase. So when you supply those three phases into here, basically you're supplying these. So there's your green, your black, and your red. That's how the sine waves enter in each piece will look. Okay, so three separate sinusoids, 120 degrees apart, goes into your, you call it your stator. Okay, so there's your stator, which if you look on your lab on the ground, is basically the ones we actually see in the coils inside on the surface itself, and you have the big space in the middle. But these on the outside, the coils you see there, that is your stator windings, and it's basically just three windings at 120 degrees apart like it. Okay, so you have a three-phase power going into here. When a three-phase power goes into here, what happens is it kind of gives you something called a rotating magnetic field. It looks like it physically rotating, but it's not really rotating. It's just the north and south kind of alternating in such a way that the entire rotation will kind of rotate this way. So yeah, put a rotating magnetic field on the stator. So you can just picture the physically the stator coil is not rotating, but the magnetic field on the stator it rotating. Okay, kind of looking like north and south just going around in a circle. Okay, physically it magnetically moving around, but physically it's still the same. So you get a rotating magnetic field. That's really all that the stator do, which is what you call your synchronous speed. So your synchronous speed is basically just this, the speed at this rotating magnetic field rotating at, which is your stator magnetic field. So when you supply a three-phase power to three coils at 120 degrees apart spatially, it creates a rotating magnetic field. And that magnetic field will rotate depending on the frequency of the supply. Okay? So you call that synchronous speed. So far we know three-phase power, three single phases going into three single coils 120 degrees apart, and when you do that, you can get a rotating magnetic field going around in a circle. And then as that begins to go around, just to keep it kind of simple, I'll just use two pole pairs, right? So you know this going around in a circle like it. He's spinning. But now inside you have something called a rotor, and you have two types of rotor. You have your squirrel cage and you have your wound rotor. And this in lab and wherever when you use a squirrel cage. And all this squirrel cage is just a bar. It kind of looks like this. It's just bars. Yeah, just bars. This is just bars that are shorted together. That's why I call it a squirrel cage. It looks like a cage when you look at it like from the outside. It can look like a cage though, like this, but you just bend it to make a circle. So it kind of look like bars going around in a circle. So I call it a squirrel cage. Yeah. Now this inside here. So follow me here. So you know you have your rotating magnetic field going around. Good. Inside here now, when you have this rotating magnetic field going around, remember this is actual magnetic field and it will be cutting the bars here. So when you have a magnetic field that cuts in a bar, it induces a voltage. So when you have a magnetic field, it gives you a voltage, or you can say a EMF, an induced EMF. And that induced EMF in the bar will create a current, a circulating current. Current, but the bars shorted together. So because the bar is shorted together, you actually get a current in the bar itself. And when you have a current in a bar, a current will give you something called a magnetic field. And you call this magnetic field the rotor magnetic field. So the stator magnetic field inducing a magnetic field in the rotor. Okay? So remember these north and south going around in a circle, right? So now he gonna induce its own little magnetic field. So you have a north, south, and I just use one for now, which is actually millions, but just one for now. So what I will try to do, remember what opposites attract and like repel. So when you actually induce this little magnetic field here, this north will try to attach onto this south. It will try to, obviously it won't be able to, but it will try to, so it will lock onto it, and obviously this north repelling it this way. So because this repelling it to go in this direction, and this south pole attracting it to go in this direction also, you ended up with it going around. Same thing at this side, this south pole repelling this south here, and this south will try to attach on to this north pole here. So all in our picture, this happening for each bar. You have a north and a south, and if you have like 50 bars, or whatever the case is, you have basically the north and souths for each of them trying to latch on to a north or a south, depending on what they are. The north trying to attach to the south, and the south trying to attach to the north. And obviously, the souths repelling the souths, and the north repelling the norths. So, what will happen is you can clearly see that it will rotate in this direction. But it will rotate, but it will never rotate at the speed of the black one, which is the synchronous speed. As you clearly see, because if you're running down somebody, you have to be behind them, which is basically what the north's doing to the souths, and the south's doing to the norths of the stator magnetic field, trying to catch it. But the process of it trying to catch it, giving it the energy to actually catch it. So you can't catch it, because if you catch it, everything done. The motion stop. Right? Because remember, you have the magnetic field, and this is cotton. The cotton is what giving it the voltage and the current and the magnetic field. The moment this cotton stops, and the cotton will stop when the north and the south, when it catch it. When it catch, it basically gonna be rotating at the same speed. So it have nothing to run down, so you have no cotton going on. Somebody's trying to raise a hand. Right, yeah. So yeah, so nice. So once you have no cotton, you have no voltage, you have no current, you have no magnetic field. So it wouldn't stop rotating at that point, but you kind of hear the motor kind of jolting, you hear it go zoom, 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 zoom. It will kind of be catching up to the speed and then slowing back down. Because technically, when it catches up to the speed, the EMF will stop. And if the EMF stop, the speed will kind of drop a little bit because you're reducing the EMF. And because it reduced, it slowed down, and now the slip will kind of decrease back, and then the cotton will increase, and it will just speed back up again. All you have to think about for induction is cotton. The more cutting you have, the more induced voltage, the more current, the stronger the magnetic field, and the stronger this magnetic field is actually, the stronger it will actually try to attract onto the synchronous speed. Yeah? So remember, trying to catch it, but it can never catch it. Okay, if it catch it, everything done, which means the cutting done. Always remember that when you're thinking about induction, you need a relative difference between the synchronous speed and the rotor speed. You need that difference. Why? Because that difference is what gives you the cutting. That is the reason why. Okay, you need the cutting to get the induced EMF, to get the current, and to get the magnetic field. And that magnetic field is the magnetic field that's trying to catch the south and the north pole. The moment this magnetic field disappears, it have no more catching. Everything just drop. Realistically, this will never happen in a motor, but it could happen if your motor giving trouble or something like that. It could happen. Okay, we kind of hear it speeding up and slowing down, speeding up and slowing down, speeding up and slowing down, which means it catching up to synchronous speed. And when it catch up, the cutting down, it slow down, and because it slow down, it will cut more and the speed will go back up. So that is basically what happening. Okay. Yeah, so that's basically the concept of the induction motor. Three-phase rotating magnetic field cuts the rotor bars. When it cuts the rotor bars, it induces a voltage, which then creates a current, and this current creates a magnetic field, and the magnetic field latches on, but it have a relative difference between the synchronous speed and its spins. That's basically what happens in a nutshell. Okay, cool. So part one there. So the next thing we have to know, or actually have to remember, is actually the equivalent circuits for the induction motor. So let's get my notes. Cool. So skipping all the derivation, they really need to know how to derive the circuit. The circuit I have to remember is the first one. You have your input. So the input is phase voltage. In the question, they will most of the time always give you a line voltage. So if you know you want to get phase from line, you just divide the line voltage by root 3. So that's how you get a phase voltage. Most of the time in the question, they will give you a line voltage. How you will know? Because in order to give you a phase, they have to say 230 phase. They will literally say the word phase after. If they don't say the word phase after, that means it's line. Yeah, just keep it simple. So most of the time you have to convert it. They will most of the time never give you a phase voltage, because when you measure it, you actually measure the line voltage. You have to physically convert it. And in the lab, you actually send in 3 line voltages. But in the motor, because it's connected in a star configuration, it will do the conversion for itself. Yeah, where you send in line voltages, 3 lines. Anyway, so yeah, so that transformer, so basically the same concept. You have your losses, same losses as before. So you have your RO and your GXM, and well, this is your IM, IO, and you have your I no load. If you remember, transformers is the same steps. To calculate those, is literally the same thing. So where it changes is this part. So in this part, you still have your, so in this case, this is your stator. So this we'll call your RS. And then you have your stator XS. Different from the transformer, but it's similar. In this case, it's not R1 and X1, it's RS and XS, which means it's your stator copper losses and your stator um, magnetic field losses. Okay. And then after here now, this is where the circuit kind of changes. So at this point here, physically in the circuit, you have no physical connection between the stator and the rotor. You have a gap. There's just space. And the magnetic field that rotated cutting that field, but also cutting your rotor bars. So after at this point here is something called your air gap, which is your PAG point, which is your the power in your air gap point. So basically this power, if you look at it, you have your input power. When you minus the losses in the stator, you end up with the power in the air gap itself, which is the power that will then cut the rotor bars. Okay, so we have here, and then you have our space, but obviously in the circuit is shortening. And then after that now, you're on the rotor side. So it's the stator side, and now we're on the rotor side. So on the rotor side, you have here, it's similar, but you have here GXM. This case will be GXR prime, because what they did in the derivation, they just brought the rotor side onto the stator side, so you just end up with one circuit, okay? So it's GXR prime, and then on this side now we end up with R resistor, this resistor is RR prime on S, okay? And then it joins back to the first piece. So this is your equivalent circuit here. So it's basically just, if you have I1, the good thing about this circuit is I1 goes through RS, GXS, JXR prime, and R prime, RR prime on S. It's the same current going through everything. So it's similar or a little easier than transformers because it's the same current you're using going through all of them. Yeah? But it's the equivalent circuit that you have to remember. Okay? So, and most of the time I have to draw this equivalent circuit with the values. It's cool. So the next thing we had to do was obviously equations. Nice. That's not. I'm gonna run in the washroom quick. Come. Alright, cool. Nice. Sorry about that. Yeah, so let's go through this quick. So you have the equivalent circuit and you have your equation. So these are the equations you need to know. So we know the synchronous speed is ns and the rotor speed is nr. So let's run through this quick. Make sure you remember these things because it's basically a toolkit for the entire topic. So your synchronous speed. So in the question, they will normally give you a pool. So they might give you a pool pairs. So you just read the question and note which one they give you. So if they give you pools, if you want the synchronous speed from that, it will be 120 by Fs divided by the pools, which is just P. 1.1 is when they give you the pool pairs, so it will be 60F divided by the pool pairs, normally poofies. So these are your first two, and well, by default, you have your 2, which is just converting it to omega s, which is just ns by 2 pi and 60. Same concept as before. But you could get a different equation with this, but all in all, I wouldn't tell you that because I think you could figure it out, right? If they give you ns, it would just be this equation you're using, okay? You just multiply the ns by 2 pi and 60 and it's an angular speed. So that's basically what you'll be doing there. And then the third equation is your slip equation, which is just ns minus nr on ns. But by default, we also have the one with omega s minus omega r on omega s. So that is the first one that I will be doing. And then we continue the others. See which other ones I had. Yep, I think I had more. Yeah, the last one is island. So if you look at the circuit itself, you have this voltage here, which is the same voltage here and here. So basically, if you want the current through this entire branch here, it will be the voltage divided by the sum of all these. So that's divided by Rs. That's the first one, plus R prime on S plus J XS plus XR prime. So that's the sum of both of them. Okay? And that is basically the four or the main four equations that you had to know. Okay, so next thing we'll run through is something called the power flow. If you remember the power flow, you're basically set for induction. It doesn't matter which one you start with, you cannot go anywhere. Honestly, you can go anywhere you want to. So I'm just getting. So the first thing I start with is Pn. Now we know Pn if the equation for the root 3 V line I line cos theta. So you have your input power. And once you go into the input power, you have your first set of losses, which is your copper losses, which is actually in the core itself, which is RO. So from the circuit, you have real losses here. So you call that your copper. So your stator losses, and basically that is just IO squared RO. Same thing from your tests. And that is your first set of losses. And after that set of losses, you have another set of losses, which is your core losses, which is basically just the losses across here. RS, same concept. It would just be I1 squared by RS. Nice. And then after that now, you end up with your air gap power. So basically air gap power is basically when you subtract your copper losses and your core losses from your input power. Okay? And we have a nice equation for this, which is just I1 squared by RR on S. That's a nice equation to know. So you cannot get your air gap from the I1 current, and what RR prime will give you that in the question, so you don't have to worry about that. And we'll continuing. So now you're on the rotor side. So on the rotor side now, you basically go and continue the same process. So the first set of losses on the rotor side is your copper losses. So remember, we subtract this, we ended up with here. And then the first thing you had to subtract, you ended up with your RR loss, which is real loss. Remember, losses is always real, right? You never consider your losses for J. Okay, so you can kind of eliminate that from the circuit when you're talking about losses. And I just I1 squared R prime. And let's have another equation you could use to get this, which is S PAG. So you have two equations that you could use together. Cool, and we just continue. So far in the circuit, we are on this side here. So the cool thing is after you subtract those that are losses, you end up with your mechanical losses. Yeah? Yeah. Right, so you end up with your mechanical losses on this side. Yeah? The mechanical losses, which is just PMAC, is basically, if you want to think about it, is your PAG power minus your copper losses. If you look at it from the power flow. So when you end up with the PAG power, when you subtract this, you end up with your mechanical losses. So basically, see the equation from the power flow, and it have another form of it, which is relating it to the S and the PAG, which is just the PAG by 1 minus S. So you can get PMAC from your PAG once you have your slip. So once you have your slip and you get power, you can get PMAC. And your copper losses if you wanted to on the rotor side. Yeah, and you're almost done. So once you have your mechanical power, the next thing you subtract is frictional windage. And note this frictional windage is across the three phases. So there's a three-phase loss. So in that three-phase loss, you have to consider that at the end, this mechanical power here is single phase. So you'll have to multiply the mechanical power by 3 in order to use this. So just be careful when you're doing the question. When I give you a frictional windage across the three phases, not just one. And well, once you subtract a frictional windage, you get output power. And basically that is it. And if the asks for torque, there's only one equation for torque. So P out is equal to T omega R, which is the same thing from when you added the transformers and stuff. So if you want to make TD subject, the formula will be P out divided by your rotor speed. And there's the power flow that you had to remember. Once you remember this, you're set. So if they get input power, if you want to get PAG based on the values they give you, I1, and have an equation to get I1 from before. RR, you will get that from the question. They will literally tell it as you will see in the question, and you can get everything you want. So, advice, remember this power flow. Because once you remember this power flow, you could get from anywhere, well, you get to anywhere, from anywhere basically, right? Input power, the two losses on the stator side, and once you reach your air gap, you basically reach your rotor, and there's the stator side. So the PAG is basically just the power that the rotor seeing, or the rotor bars seeing, okay? And I mean, that's basically all the equations you would need to know. Honestly, I have no more that you would need to know when it comes to this topic. Yeah. So remember these. So these four and this power flow is basically a bread and butter. Everything else is just add-ons based on whatever question he basically wanted to do. Right? So one
So you
more.
could just scroll up to the
Yeah,
first.
somebody asked something.
You could just scroll up to the
Yeah,
first, yeah, the first part of the question.
first which this way or
Yeah, right there,
the power flow? Okay.
right there. Number 4. Yeah.
No, oh, the I1.
You see for number 4, yeah.
Okay.
Okay, thanks, I got you.
Yeah, no problem. But I would advise you to remember that one. If you draw the equivalence, you can clearly see what the equation is, right? So,
Okay.
yes, remember the equation, but always try to remember how you get it if you could. Yeah, so you wouldn't make a mistake too much, right? So with this I1, you will get the power factor and everything from it because it'll be J term in it, okay? So yeah, very cool. So one more thing is the torque equation. Okay, I'll just give you all that equation one time. So the torque from here, before we go into this one, is just 3 times your mechanical power minus the frictional windage. Reason why I'm multiplying it by 3 because the frictional windage is across your 3 windings. So because of that, you have to multiply the Pmax by 3 in order to get the output power, and you divide it by the speed. So technically, the P out is 3 by Pmax minus the frictional windage, which makes sense because remember this power flow it starts off as per phase. Once you get to the output is not one phase rotated the whole motor. It's the three phases. So you have to account for the three phases by which you just multiply it by 3 because it's a balanced system. Right? Anyway, so the actual torque equation minus in the derivation, T would just equal to 180 V phase squared by alpha S divided by 2 pi ns xr prime by alpha squared plus x squared. If you also pull out the constants, you'll end up with k. So k will be 180 is a constant. V phase is a constant. V phase squared is a constant. 2 pi is a constant. Ns is a constant. Xr prime is a constant. So you end up with 3 constants that you deal with. I mean, and with those, you can pull it apart from the t equation. And once you pull it apart from the t equation, you put k, and basically what left, which is alpha s divided by alpha squared plus s squared. Okay? And the two things you need to know from this, well, is rr prime and xr prime. That is the equation for alpha. The kind of skippy derivation what I did. Right? Because still doesn't bring derivations in exam, that's waste of time. But you will bring questions where you have to use the theory to calculate values and a little bit of theory. So the little bit of theory you need to know is the first thing from this equation is a torque speed graph. So you have omega r, which is your speed, and you have t, your torque. I'm probably gonna have to put that. Cool. The graph itself. So this is 0, which means the speed is 0, which is your starting torque. And then the graph itself will kind of look something like this. So where it cuts here is basically your synchronous speed. Because at synchronous speed, you have no torque. Because if you have no cutting, you have no induced. Okay, I went through that, I like remember it, right? If you have no cutting, you have no torque because you have no force. Okay, so that's what the graph shows. This point here, you call it your pull-out torque, and then starting torque, and this one here. There's not really a name, but it happens when your slip is 0. Which makes sense because if you're slipping 0, it means that you're rotating at the same, but trying to rotate at the same speed as synchronous. So rotate at the same speed for a fraction of a second and it will drop off when the torque just drop. Okay? And well, this your starting torque, when your starting torque happens, your slip is basically 1, which means you have maximum cutting, which makes sense. Okay? If you're starting at standstill, the moment you plug in, which you saw it in the lab, the induced current going to be the highest because the slip is the highest. Okay, so you end up with a starting torque and it will continue to increase. And now let's go back down. This region is basically most of the time where you're operating. This kind of unstable, right? Okay, cool. So how to get these values? So the first one you need to, they'll ask you to get is the max torque, a little bit of max, right? The max torque will occur when the differential of the equation is equal to 0, which is basically here. If you remember stationary points from maths, so to get the stationary points, you differentiate it and you make the equation equal to 0, a little bit of math, right? But just to skip how we get that, that will happen when the slip value is equal to the ratio of RR on XR, which basically happens when S is equal to alpha. Remember, this is alpha, right? So if you calculate the ratio of this, if you get 0.4, you will use that value of S in the equation to calculate the starting torque, okay? Or in this case, the max torque, sorry. Yeah, that's basically the concept for your max torque, which you can clearly see here. That is your max torque there. You don't have to do the differential and all that, right? You're just doing that and look with the actual value. And what they found out is that that torque will actually occur when your slip is equal to the ratio of your R and X. That's really what you have to remember. You don't have to remember all the derivations and things. And the starting torque. So your starting torque occurs when S is equal to 1, which I mean, clearly is what I hate. Okay, so you just use the equation and plug in S. And once you plug in S, you end up S as 1, you remember, with K alpha divided by alpha squared plus 1. And well, you have all these values already, so you can get your TS. Okay, that's really all the equations you need to know. Starting torque equation, max torque, the torque equation, and then from the power flow you end up with a power equation, which is this. Okay. You all good? So if everybody good, let's go straight into the questions. Let's get a solution. Okay, cool. So if we read the question, the first thing I want to tell you all is that anytime they give you these things, most of the time it's already referred to the stator side. That is always how they will give it to you. So you don't have to worry about referring it and all that. They will always give it to you on the stator side. Okay, just keep that in mind when you do any questions. Cool. So read the question, they give you a three-phase 128 RPM. So this is your NR. They give you 60 and 4 poles. These two things is where you use to calculate NS. They give you a pole, so you use the 120F on P equation. They never give you a pole pair, pole phase. Well, for 60 line, well, we kind of give you a hint here, right? But in the question, they will just say this without the LL. They just say this. You have to know that is line, okay? Well, star connected here. You will never find a delta connected induction to and has the following impedances already referred to the stator side. So you kind of see them one time. So this is your RS, this is your JXS, this is your RR prime, and this is your JXR prime. Kind of seeing everything there. Right, one supply with a rated voltage, or the load current, so give you a no load current. So this is IO and XM. Remember the no load is IM minus, oh, sorry, arrow, IO minus GXM. Yeah, so I kind of gave it to you right here. And well, they gave you the rotational losses. Remember, these losses are across the three phases, okay, not just full phase. Draw the equivalent circuit for the machine. So very simple. Two dots. This will be 460 on root 3, because remember, it's phase voltage you're supplying in. And then you're coming down. We don't know what these values are as yet. And you continue. So you have, they gave you, I think they gave us that. Then you have your air gap. Then you have this and this. And you come back around. So you have your GXM, which we had to calculate. RO, which we had to calculate. You have your, I think they gave us RS, 1. They gave us GS, XS, right here. And the stator, 0.5. So this will be 0.5 on S based on the equivalent circuit. Remember, it's RR prime on S. So this is RR prime here. And well, this is, yeah, GXR prime, this is this 3G. So don't forget that, right? Remember the equivalence circuits for the RR parts. You have to divide it by S. Okay, so don't forget that. Okay, so piecing apart everything, so we have this. So the first thing we have to calculate is the R1 the XM. Okay? So Just from before. In this case, they gave us the current. So if they gave us the current, we just go straight to calculate the resistances, right? So RO will basically just be your V1 phase on IO, and in this case is 460 on root 3, remember it's phase, and IO is 0.5. Remember from the equation, this is IO and this is IN. Okay, when you do that, you end up with 531. The top decimals, but when you write all that, right? You can always write it to two decimal places in the exam. And then your XM, so it'll be V1 divided by IM. And once you do that, it'll be 460 divided on root 3 divided by, I think it was minus 6.66 G. Anyway, and you will basically end up with G 39.84. Cool, and we have those two values. Very simple. You can plug it back into the equivalent circuits. Nice, input current. So when you have one input current per phase equation, so that is a big long one. So your input current is the sum of your no load current plus I1. Remember I1 is what here, and your I no load is here, and this is your input current. Always remember that, right? Your input current is not I1. So if you use the I1 equation and say that is the input, you're wrong. Okay, you have to add the no load current. So that's how the current does work, right? They already give us the no load current already. So we just have to find I1 and then add them together. So I1, using the same equation, I'll just skip the value. So it's V phase divided by RS plus RR on S plus G XS. So we have 3 and 3 straight from the equation. So you see we have to calculate now is our slip, which is S. So S is NS minus NR and NS. We have NR from the equation. We don't have what NS is, but we could calculate it. NS will be 120. The frequency they gave us in the question was 60, and the pole is 4. So 120, 60, and 4. And that will basically give you 1800. Yeah, so in this case, up here will be 1800. Subtract the 1728 divided by 1728, and you basically end up with the slip being 0.04. So we have our slip, so we plug it back into here. And we end up with,
So
yeah, yeah,
it won't be divided by 1800 if it's
yeah, yeah,
NS
yeah,
on the bottom.
yeah, yeah, yeah. Thanks, yeah, very correct. Yep, yeah, 1800. Nice. You get the, well, I'll get the same answer, because I write 1800 in my paper. But thanks for letting me know. Yeah, that was correct. You also get the same answer, yeah. I did the calculation with the 1800 underneath, so don't worry. Yeah, anyway. So when you plug it back into here, you end up with I1 being 16.43 minus 7.3 G. So that is I1. All we need to do to get IN is just add it back to the no load. I think the no load was 0.5 minus 6.66 G, and you just end up with, if you write it in phasor form, 17.98 angle minus 23.96 amps. Okay, which I think is 16.43 minus 7.23 if you write it in complex form. So that is your I. Concept is the same equation for I1, just you had to add it to your no load current. And if you need your no load currents, you just have to go back up. Depending on how they gave you the question, if they gave you the resistances, you can calculate the current because V is equal to IR. It's the same concept that you're doing. In this case, they gave us the current and you have to calculate the resistances, but they gave you the current. So you don't have to go anywhere else to get the no load. Yeah? Right, so what's the next part? Right, the air gap power per phase. So we have a nice equation that you can just get the air gap. So we have S and we have I1. So you just use the normal PAG equation, which is I1 squared by RR prime on S, which is the beauty of equations. Because if you notice, you have these things, so I just use it and then. So I1 numbers this here. So if you're squaring it using the real part, so we could just square it in that form. So it'll be 16.43 minus 7.3 J squared, and your RR is 0.5 on S, which is 0.04. Yeah, straight from the equation, nothing different. I want to see that I end up with 41 watts, or 4041 watts. Raw equation, because you know you have I1 already, and you have R, and you have S. So the easiest one to use would be this one. Yeah. And then next one is output torque. So the output torque, you have to remember that your output power is 3 times your Pmax minus the frictional windage. So that's the first thing they have to get your output power. And from your output power, you can calculate your output torque, because P out is T out omega R, so you just make T subject at the formula, so it'll be P out and omega R. So the first thing we need to calculate is Pmax, because they gave us the frictional windage losses in the question. So we have S and we have PAG already, so we could just use the equation which states that Pmax is PAG 1 minus S. Yeah? Just knowing what we have. So it will be 40.41 watts, or 1 minus S, which is 0.04. Yeah? And once you do that, you end up with 3879.36 watts. Now once we have Pmax, we just go back on top here. The frictional windage losses across the entire motor, which is across the 3 phases, was 300 watts. So the output power will basically be 3 times 3879.36 minus your 300. Um, okay, that's divided by the speed on time. So this is omega R, so it'll be 1728 multiplied by 2 pi and 60. So let's be careful, right? So this will be the whole thing. So 3 by Pmax minus 300 is your output power divided by your rotor speed. And once you do that, you end up with 62.66 Newton meters. Okay? Same power flow. The output power is 3 by Pmax minus your frictional windage losses. Now the torque is divided by the angular speed, not the RPM speed. So let's be careful when doing that, right? And what's the last one? Shows efficiency. Yep, efficiency. So the efficiency equation doesn't change that much. So in this case, we know what the output power is. So we could use the equation that have P out in it. So it'll be P out and P in, and we could express P in as the output power plus the losses. Yeah? Same. This is always the easier one. most of the time you will have your output power because they'll ask you to calculate your torque. So, which means you have your output power already because they already have another way to calculate your torque without calculating your output power first. Alright? So, most of the time, this is what you have to use, okay? Um, in that case, just be we calculate the P out already. So this will be, if you actually plug this value in, it'll be 11,338.08. Just part on top here. Because I didn't calculate it before, just put the whole thing in the calculator and divided by 11,338.08. And we just add the losses. So where are our losses in our circuit? So the losses are all the real losses. So you have a real loss here, which is IO squared and R. Remember, power is I squared R. Then you have another real losses here, which is I1 squared by RS. Then you have another real losses on this side here, right? But you're not including the S in this one. You're just using the 0.5 flat. Just be careful with that, right? Just like the transformers and all them, the same equation. So the first one, IO squared R, that's the first set of losses, and the other set of losses will be the losses the copper winding in the stator. So it'll be the I1 squared RS, and then across on the rotor side is the same current, but you have your RR prime losses. You only have these three losses. You do not consider reactive losses in here. Losses efficiency is based on the real losses, which is all the real components in your circuit. So don't go and put any J terms in your circuit on there. Yeah, and just remember for this RR part, it's not R prime R and S, it's just RR, the actual resistance, right? The S part, the reason why they modeled that is because they try to add in the load, but the equivalent circuit is just RR prime. They just put the S there because the slip kind of dependent on those, okay? So just keep that in mind. And we'll just plug in your values. So the way I used to do it is the copper losses, which is the stator and the rotor part. We call it PCU. It would just be 3, because remember there's 3 phases, by I1 squared by RS plus RR prime, which is basically just this here. You kind of calculate it one time. However, we know the PO, like you say PCU PO, is 3 IO squared RO. Yeah? So remember, as across all 3 phases, right? So you can put 3 here also. Right? That'll be the full efficiency equation that you need to know. Okay, so P out, 3 times RO, so remember there's 3 phases, and your lab you conduct the investigation across 1 phase, but realistically it's 3 phases. So you have to multiply it by 3 anytime you're doing any efficiency calculations, right? Because the efficiency is the entire motor, not just 1 phase. So you just multiply the losses per phase by 3. Okay, so and with this, yeah, I mean, at the end of the day, you'll end up with 11,338.08 all divided by 11,338.08. So the R, the sum of the R losses will be 1454, and then the IO losses, the smaller one, will be 398. Yeah, and once you plug all these into your calculator piece by piece, you end up with the efficiency to be 84%. Okay, yeah, well, plus, so it'll be 698 based on if you're using this. Yeah, nice, and that'll be, so the same concept as before, just a little different, right? Somebody asked me a question.
So I had a
Yeah,
question about the power losses due to friction and windage. Does it have any like equation for that? Because I know they
no,
just give us the
no,
300
no
watt.
equation for that. That frictional wind is based on the environment the motor is operating in.
So they'll always give us that.
Yeah, because that's a nameplate parameter. Yeah, it have no it have equation, but there's not physics, but you're doing mech. But the frictional windage value, they normally give it to you in the question.
Okay, sir.
Yeah, you know how
Thanks.
to like calculate it or nothing like that. Yeah,
All right.
probably in all your degree, you probably have equations that you could use to calculate friction and things, but we don't need to do that. Yeah. And on the nameplate for all motors, they give you the friction and windage losses, because that's a constant. That will always be there once you operate the motor. Yeah. And well, the windage is basically if you're turning something in the atmosphere, you have friction due to the particles in the air. So you have to actually overcome that to actually move the object. Because as an induction motor, you see it in elevators, vertical lifts, like all those things. If you're operating it in an atmosphere, you have particles, which is atmospheric pressure, coming down or just around the object. So in order to actually turn it or move it, you actually have to overcome that. So that is the windage and the friction part. Yeah. All right. Any more questions? Alright, cool. So that is it. Induction, you could get marks for induction and synchronous, right? Um, Make sure to get marks in that, all you need is to memorize the equivalent circuit, memorize the power flow, and memorize these equations for the torque questions, with the max torque and stuff. Because most of the time you just ask you to calculate the starting torque, calculate the max torque, which you just had to write down max torque occurs when dt and ds equal to 0. When s is this, you will have all these already, just like how the question gave us it. You'll have it already, and you can just calculate your values. The reason why I picked this question specifically is most of the time they ask for these over and over. Yeah, you need to do all the questions, but doing all the questions will just help you with speed. Yeah, you don't need to like do all if you already understand the ins and outs of a few. Yeah, but doing it will help you with speed. Yeah, but they normally ask you for the same thing over and over. And what will help you if they ask you for different things is the power flow. Because with the power flow, you can clearly see if they get output power, you can actually work back. So if they get output power, if they ask you for PMEC, first thing you have to do, okay, this output power is across three phases. So if they want the per phase, you divide it by 3 to get the per phase. And then, yeah, you could work with it both ways. Like the easier way for you to do it, if it's like this, just subtract your frictional windage from your output power. And once you do that subtraction, then divide by 3 to get the per phase PMEC. Remember, PMEC is per phase, right? If you're doing the equivalent circuit, it's per phase. So the output power is across three phases. The friction windage is across three phases. So output power, you add back the frictional windage because you subtract it here. So when you add it back, you get the PMEC. And once you add the PMEC now, you keep going back. If you add the rotor copper losses, you end up with your air gap power. And if you add the core losses plus your copper losses, you end up with your input power. This is a power flow. So you could go from anywhere to anywhere. And they love to bring these equations as PAG1 minus S. Those equations are very important. They will really bring these because these involve more computation because you actually have to calculate values and stuff. But once you have a PAG, they will always ask you to calculate a PAG. Once you have PAG and the slip, you can get the PMAC and you can get the output power. And once they give you the friction and windage losses, because the same flow. PMAC here, once you subtract your friction and windage, you have your output power. PAG, it links PAG to PMAC once you have a slip. Okay, right here. So it links the two of them together. So the rotor part, very repetitive. It only have like three equations. The first one is your PAG, which giving you your copper losses, and PMAC. And PMAC will give you your output power, and from there, you go anywhere you want to. So spend some time memorizing your power flow, become comfortable with it. So depending on what they ask you, you wouldn't be shocked if they ask you to go from, if they get the PMAC and they ask you for PAG, you wouldn't be shocked. You know, okay, you have an equation to calculate PMAC and PAG. PMAC is equal to PAG 1 minus S. Did they give me S? Okay, I have to calculate it. Plug it in the equation, pow. Simple. If they ask you for the copper losses on the rotor side, you're looking at it, they ain't give you no values, but they give you PAG. Well, you should remember, okay, well, the root of copper losses is just S by PAG. And you go on your way, which is the power of memorizing equations. Most of the time in the question, you will have to calculate I1. Do not mix up I1 with your input current. A lot of students have made that mistake and throw away your marks. Your I1 is the current after you subtract your no-load current. Yeah, just be careful with that. And with your no-load current plus your I1 will give you your input current. So just keep that in mind, right? And well, this part here, remember, if they give you these values, you could calculate the current because V is equal to IR. So this part here will end up with your IO equation, which is V phase divided by RO will give you IO is equal to IR. And this side here will give you a imaginary part, which is the minus J whatever. And when you put both of them together again, with your I no load. That is if they give you the resistances. Yeah. So just make sure and look to see what values they give you so you will know where you could go and what you need to go where you want to go. Okay? I will pose pairs. Omegas, same powerful. Equations, powerful. That is all. So most people normally do well in induction and synchronous because it's so repetitive. So only have so much ways you could change it up. So try to get your marks in it. And if you understand induction, you will understand synchronous. Because synchronous is just the opposite. With on a squirrel cage, you actually just put in a magnetic field inside and you're inducing the three-phase power on the stator. It's basically just the opposite. So it's the same kind of concept, but just instead of you turning instead of the stator magnetic field turning, you're turning the rotor part, which giving you that three-phase out. Okay? So what I would do, so that's it. So what I would do is